So the last part in the HQET that I will try to cover is showing how the reparameterization invariance in some way gives you the idea of restoring Lorentz invariance. Because we are working in one specific frame, let's say the hadron rest frame, that already breaks the Lorentz invariance. And the idea of the reparameterization invariance is to show a non-relativistic way or a realization of the Lorentz invariance in the non-relativistic EFT. So RPI, it's called. This is ultimately Lorentz invariance. In NREFT. So when I'm talking about NREFT here, basically means HQET. It's fundamental theory is QCD. So before arriving at the HQET Lagrangian, the point was I wrote P mu as MQ V mu plus K mu. So where again my K square is of order lambda QCD square. And V square is 1. So V square is 1 from the on-shell condition. That I want to have P square close to MQ square. Or it's normalized thing. So the point is this, where do I split this V nu? I mean, is this V nu unique, or can I add some perturbation to V mu? People have difficulty in seeing or something. So the question is, can I add some perturbations to V mu that can change things or go to a different frame? Ideally, the physics would be independent of any frame that you want. Let's say somebody was working in lab frame, the V mu is something there. Somebody is working in the rest frame, V mu has specific choice. Somebody is working in another V mu frame, there the value of V mu is something else. So the physics should be independent of it. And ideally, what would we expect is that any change in V mu that we make the physics should remain the same. My HQET Lagrangian should remain the same as the HQET Lagrangian. It should not change out because this V nu is not something unique in a way. So, in other words, what I mean to say is that this decomposition is arbitrary up to corrections like delta V mu. So V mu going to V mu plus, let's say, epsilon mu by M. So this is my delta V mu here. Maybe let me define it more properly. Where again, I want epsilon square to be of order lambda QCD square. Okay. So let's say the kicks from the soft gluon exchange in the heavy meson. In one case gives me a V1, in another case gives me a V2, and this is the relation that would connect my V1 with V2 in a way. So any change in V mu, in order to keep the heavy quark momentum same, I can So change in V mu is V absorbed as K mu to K mu minus epsilon mu. So, yeah. And this basically gives you that in a frame where I have P prime mu, P prime mu, which is MQ V prime mu plus K prime mu, and I substitute, let's say this is 1 and this is 2. I substitute these expressions. What I will get is MQ V mu, plus K mu, which is my P mu. So I could have started with a V1 whose definition is given by V prime and a K1 whose definition is given by K prime. Or I could have started with a frame where my definition of V is just this V and the definition of K is just this K. Ideally, the goal is that in this non-primed and the primed coordinate, the frame, the physics has to remain the same. This is what we are aiming for. So because V square is 1, I also demand that V plus epsilon by mu, so which is equivalent to V prime square as 1. And up to order epsilon, we get this condition that V plus V dot epsilon is 0. Okay? Now, we also know that 1 plus V slash by 2 HV is HV. This implies V slash HV is HV. And so any change I do to the V, I have to also do the change in the field because the field is now transformed to a new frame in the prime coordinate. And so I define a change in field as HV plus delta HV, where delta HV is order epsilon for me. So if you do that, use this equation. So V slash plus epsilon slash by M, HV plus delta HV by, as at order epsilon, what we get is 1 minus V slash. We get a constraint on delta HV, which is epsilon slash by M HV. Okay, everything fine up to this point. So basically, this constraint is giving me what this delta HV is, or what I can define for delta HV. In principle, I can have many choices. Like I said, I can go into a frame where I could have as many where I could have different choices for the delta HV. But let me a simple choice that would satisfy this equation. So simple choice here means a specific frame. Of reference, and the one that would satisfy this equation is this. So you should try to see whether this one satisfies this equation and try to verify by yourself. I would not delve into the detail of it. So now we have defined everything, how the field should transform, how the velocity should transform, and now the goal is to see how the Lagrangian is going to transform and demand that the action has to remain the same. That's what we mean by saying that the physics has to remain the same. Sorry? So I started with a frame where I'm defining my V square to be 1. My epsilon is a small parameter. I'm now in a new frame V prime where I still demand that the normalization of the V is 1. And that up to other epsilon will give me a V dot epsilon equals to 0 condition. I mean, you just expand it here. Yeah. I mean, this is V square plus, yeah. Yeah. The small amount is important because you do not want to break your, you do not want that the change in V mu is of the hard scale. Yeah, you want that the changes are small, which are coming from the interactions with the light quark or the gluon. This is just the normalization condition I'm demanding. Lagrangian? That's what we'll see how the change in Lagrangian is.
A moves and B moves, then the Lagrangian.
Yes.
To reparameterize both HP
And V together. So if my V is changing, my field has to change. And the change in field has to compensate with the change in the V in some ways. This is what we will see.
The scaling is two different coordinate describe the same physical.
So V is, yeah, I mean, V is parameterizing, like Namit was saying, V is parameterizing my field, yes. You have to change it. You mean why this V dot epsilon is non-zero? I mean, this is the constraint from the normalization, yes. I mean, I've demanded, I'm starting, yes.
Say that why we do it. If you have chosen a different V, let's say V1, that should also describe the same. It means that the slightly different V, slightly different V, slightly different choice of V, to end up making a slightly different choice of K. To keep the left hand side. But that means the
No, but the thing is, no, what you have to understand that, like, no, he's meaning that arbitrary, I mean, the point is that, so see, the point is that my P square has to be close to MQ square, yes, in any other frame. So my P prime square has to be close to the MQ square again. This is the on-shell condition. I'm describing the fluctuations of heavy quark around the on-shell condition. Yes? So what I meant was, if you do P square, this is MQ square plus some fluctuations of order lambda QCD square. In the infinite mass limit, for example, this is, okay, this is small. This should also hold same, which means my V square has to be constrained. It is the on-shell condition that is constraining the specific way of transformation. I always want to have my heavy quark on-shell. in any frame, whether I work in prime, whether I work in any frame, I want to have my heavy quark on shell. So that condition has to be satisfied irrespective of any frame you work, which means there has to be some constraint on V and epsilon in some ways. And as soon as you change V, you have to change field.
Put that like A square is all order of the binding energy lambda.
Yes.
So if I change K by epsilon, that virtuality is also order of lambda. So it looks like that side you get is order lambda QCD square. But the difference between them, it's multiplying an M, a large mass, right?
Yes.
So it is changing things in higher order. V dotted with epsilon, that gives you much bigger mass to the system.
Yes.
So you force the linear term
To be zero.
and that forces the rest time. All you change is the 3 vector direction.
Exactly.
And then the correction is coming at the square, right? A square y.
So now we have basically, the point is that all the set of transformation that I would want is V mu to V mu plus epsilon mu by M, H nu to go as H nu plus epsilon slash H nu by 2M, and H nu bar to go as, wow. So just give me a minute. I forget what is the. Yeah, so. s- 2M. This here. Just give me a- Okay. And now you basically substitute it in the, you do the, you take the heavy quark EFT Lagrangian, substitute it, and the transformed Lagrangian that we get, LHQT prime in the prime coordinate, is H nu with I V dot D H nu plus H nu I epsilon dot D by M H nu minus C2 D pop square over 2M H nu minus C2 H nu I epsilon dot D pop over M H nu. And let's not go to the higher order terms. So basically this gives me that this is my usual HQET Lagrangian, except there are terms like, well, I think this is D. Except I get a corrections which is plus 1 minus C2 plus order 1 over M square. So you just substitute it and you will arrive at this point. Okay. So let me define a simple thing here. Epsilon dot D bar is epsilon dot D minus epsilon dot V B dot D, which is epsilon dot D because it is 0. Okay, so basically I want my LHQ2 prime to be the same as the LHQET up to order 1 over M, okay? This means the C2 is fixed. I don't need to do any loop calculations, and I fixed my C2 to be 1. So this is what RPI is giving you, this constraint, that the coefficient that is coming in front of the kinetic energy in the HQT Lagrangian is fixed to 1 at all orders in alpha s. This I demonstrated up to order 1 over m. But if you go to 1 over m square, which will require a bit of tedious work, you have to notice that the transformation of the V mu also depends on 1 over m. So the V nu transforms as some epsilon mu divided by m. And so when you do the 1 by m square conditions for the HPT Lagrangian, there would be 1 by m coefficients or 1 by m terms in the Lagrangian can mix with the 1 by m square terms. And again, we would demand that the HPT Lagrangian is invariant. And one such conditions that would come up is, so RPI up to order 1 by m square mixes terms with different, relation between matching coefficients of the 1 by m or to order 1 by m square relates at order 1 by m and 1 by m square. This happens because V mu changed to V mu plus epsilon mu over m. So this m dependence in the change of V mu is what is giving the relation between 1 over m and 1 over m. So one such condition that comes up is 2CF minus CS is 1. So just to recall you, the CF was term like h bar nu s dot b by m h nu. The CS was term corresponding to h bar nu d cross GE by m square, some 8m square probably, or you can check, I don't remember the number here. So the CS was the coefficient in front of the 1 by m square term, which was this term, B cross GE, if I remember correctly. And the CF was the coefficient in term of the spin dependent term. And if I do the RPI up to order 1 over m square, I get this relation. And so any loop calculations I have to do always has to satisfy this constraint. So this is a way to show how the Lorentz invariance is restored back in the heavy quark EFT, which is a non-relativistic EFT in actual terms. Okay, so this is like the realization of Lorentz invariance in non-relativistic theories. Yeah. Yes. I mean, you will see in the one loop calculations this connection. So, yeah.
Then what is its connection to relativistic Lorentz?
The only relation I mean, in relativistic case, the Lorentz invariance, you have P mu transforming as some lambda mu nu, P prime nu. There, your lambda changes the frame of reference. Here, V mu working in specific V nu is choosing some frame of. Yes. Here I can only shift by short vector because I am not allowed to change by hard scale. Hard scale will completely change my problem. So changing by short vector is basically changing, is in a way picking up some specific frame of reference. So this is like, in a way you think that changing by soft scale is in a way going from, like in relativistic case, where we have a vector going as So changing by soft scale is something like mimicking this lambda mu, you know. I mean, I do not know a very well answer. So Tuhin's question is, how can I see it in relation to the Lorentz invariance in the QFT? Yeah.
Zero.
Yeah.
At the from this way, we are thinking a particular view. But let me make a learn substitution on the view with the requirement that it is still close to the
Yeah. Yeah. Okay. So I think. So this would be something analogous. This would is what will probably give me the epsilon mu by m, if you want. This is what I would say. Yeah, this thing will apply to both. Yeah, I mean, because I wrote a transformation for the V mu, I'm trying to relate, like in relativistic theory, you would have a V mu in one frame and another, let's say V alpha, you would relate it by some lambda mu alpha. This lambda mu alpha is what is giving you analogous of epsilon mu by m. That is the connection I'm trying to make. So this is like this epsilon mu by m is like doing analogous of this lambda mu alpha part. That's the, in very crude way, I would say. Okay.
Gradient square
Yeah, that has.
remains the same.
Yeah, because
Originally I'm going on the shade of.
Yeah. Yes, it's because the simplest way to think of is like. Yeah, I mean, basically the point is that if you think that your heavy quark is just static, it's just fixed, I just want small perturbations to the heavy quark. I do not want things that can just really move the heavy quark away. I mean, I mean, when I went, that is sort. When I went from QCD to HQET by doing this breaking in terms of V mu, I chose a specific V mu, yes. I'm already choosing a frame to work with. And that is how I arrived at my HQET branch.
The left hand side, you ask what type of thing. Is the
Yeah.
no, not the heavy one.
No, this is heavy quark. The V mu is the velocity of the hadron or the meson. Yeah, you can convert it, exactly. You can convert it. Yeah. Yeah.
That is or
Sorry?
It's quark momentum.
Here it is written as quark momenta.
Imposition of the p squared equals to m squared, irrespective of these.
Yeah. Yeah.
There must be peculiarity. In the case, this cannot be diametrically larger than the certainly not mess up with the power. You have to make Lorentz area.
Yeah.
Otherwise, it will make power. Yeah, that's the soft thing. That's what it is. But there is more. Right? Like epsilon dot equal to the. Is imposition that p prime.
the imposition
This condition is coming from the imposition of this. You want only on-shell fluctuations around the heavy quark on-shell.
Or counting would remain the same. Because, yeah, but I could think of like p prime and normalize it to 1 and dump the rest to some k prime. But normalizing p prime to 1 is same as p prime square because
MQ square.
yeah, so that's not normalizing. That's a choice.
Choice.
M square.
Okay, this is where I stop HQET. We can go on for a long time on this, but this is what I wanted to just give you a brief understanding of the things. Now I will describe NRQED, but really it will be quick. I mean, so in non-relativistic QED, so in HQET, I have only systems with one heavy quark. But now I want to describe systems with two heavy quark. So something like chamonium or bottomonium systems, or even exotics in general. So things change there. In HQET, we only had two scales, heavy quark mass, lambda QCD. In systems like chamonium, bottomonium, there are many things. There are actually lot of scales can come up along just with heavy quark mass and the lambda QCD. So before going into chamonium, bottomonium, let's take a step back and go to the QED case to understand better. And the simplest example in QED is positronium molecule or hydrogen atom to demonstrate. Yeah. Yeah. I mean, there is a way called heavy hadron chiral perturbation theory where you can do all of this. Like you have to define supermultiplets and do all of this business. If you want, I can refer a paper, but I think it's a little bit beyond the scope of, I mean, it will take me time to go over that part itself. But just to let you the name. When you say, I mean, the scalar will come up in the P wave or the higher expression. So in very quick language, this is HQET plus type ET. Okay, so you can search in Google for, or in Inspire, you will get a reference for this immediately. Yeah, boosted HQET is where you want to have, let's say, energetic B hadron decaying and generating some jet particles out. So this is like SCET. This is, I mean, I don't know so much about this, sorry. So this is basically like you have a energetic B hadron and then also emitting these soft radiation and collinear radiations. You will face divergences associated with soft and collinear degrees of freedom. They are basically used in jet formalisms. Yeah. What change? Okay, so no, BS is not a problem for us. BC is tricky in the sense that sometimes you have to be very careful with the charm in the sense that charm will behave as light particle in presence of the heavy, like the bottom. Yeah. So you can use, so BS you can use. Yes, the strange meson is much, yes. I mean, BC bar, that's what I'm saying. If you are computing processes, sometimes the charm will behave light compared to the bottom, then this will come up. But there you have to be very careful that BC bar systems can also be studied in non-relativistic QED, because if you treat both charm and bottom to be heavy, it's a too heavy quark system. And so you have to combine NRQCD or NRQED with the HQED together. The charm system is always very tricky in a sense that In bottom case, even if you do not include spin corrections, you should be fine. I mean, the spin corrections are few MeV. In D mesons or in the charmonium systems, the corrections are generally hundreds of MeV. So you will always have to be very careful in the charm case on the observable that you are counting. Sometimes they can give you corrections up, like I said, the corrections can come up to out of 30%. So you have to be careful there. I mean, that's the point. Okay, so let us take a step back. Instead of going to charmonia, where there is perturbative and non-perturbative piece associated with the linear potential, kernel potential, sorry. Let us take a step back to understand the problem from the atomic physics side, studying hydrogen atom. So good old hydrogen atom in quantum mechanics. So there, let me just open up my notes. Yeah, so there, I am describing a system of electron plus proton. There is also positronium, which is electron plus positron bound states. Okay, so E plus E minus, E minus E plus. And here itself, it's a multi-scale system. So in both of these, you know that the energy, the binding energy is proportional to some, let's start with the length scale. So the natural length scale here is A0, which goes as 1 by M alpha. Okay, everybody remembers. My hard scale is, so this is my M electron, is Me. My proton is 1 JeV mass, so it's static for that purpose. It's a nucleus for me. It's basically like proton is fixed and I'm describing electron motion around it. My binding energy is proportional to M alpha square, or I think it is M by, just give me a minute, A0 square by M probably. Yeah. And yeah, and momentum is Me alpha. Okay. Everybody recalls the hydrogen atom, this formula. So this is what we have if you look for like Wikipedia or everything. So the alpha is the alpha QED here. Immediately you see there are scales now, different scales that are coming up into the picture. My alpha at it's probably Z mass is something, if I remember. Yeah, so there is 1 by 137. It's defined at some particular. Sorry? Yeah. I wrote it wrong. It has to be, so it has to be 1 by A naught square, but then it has to get to some dimensions. So this is, so yeah, this, I think this is the one. Yeah, thank you, sorry. So the alpha in QED, this is defined at one particular, probably Z mass scale or something, I don't remember, I'm sorry. So this is like 1 by 137 we use in quantum mechanics. So you immediately, okay, let's take it as 10 raised to minus 2. And you immediately see a hierarchy of scales into my hydrogen atom systems. So even a simple system like hydrogen atom bound state has multiple scales into my system, multiple energy scales. And the scales are ME greater than ME alpha greater than ME alpha square. So this is my hard scale. This is my soft. This is my ultra soft. This is the normal language in which it is defined. If you describe QCD system, you would have one more scale, which is lambda QCD. And then you have to worry about where the lambda QCD sits, because things will get non-perturbative immediately, very quickly. In QED systems, I don't have lambda QCD, so that's a bit of relief. But the problem is a simple situation like hydrogen atom now has 3 scales into the system. And I have to systematically now construct EFTs starting from QED such that I am able to describe my hydrogen atom at the lowest energy scale, ME alpha square. Okay, this would be my ultimate goal of the final EFT constructions, which is called as the PNR QED in some ways, which probably Professor Rishi will talk about. So let me, yeah. Yeah, that is what I was trying to do. Okay. Yes, yes. So, no problem. Yeah, so you can see this more clearly by doing the virial theorem, basically, starting with the situation. So if I do the virial theorem, then basically my P square over 2m reduced is 1/2 times R V prime of R, which is 1/2 alpha by R. So my V of R is minus alpha by R. And my energy, binding energy, is if I include binding energy at the state N, at the level N, then, or let's forget the index N, it's not important, is minus half alpha by R, because, because you use this condition and this is coming from P square over 2m reduced mass minus alpha by R condition. So this will give me this. Now, so just give me a minute. So this, where I am, yeah, this immediately tells me that alpha by R is m reduced alpha square, and P square over 2m reduced is m reduced alpha square. Clear? Okay, nothing exceptional till now. If there is, you are looking at energy with index n, there would be one more index n coming up. So some are divided by this levels n equals to 1, 2, or 3. That's kind of not important. So yeah, so this now implies that 1 by R is m reduced alpha. And this implies that if I take the root mean square momentum, this is m reduced alpha, which means I can define my velocity, which is of order, which is alpha basically. Okay, if I define my P, if I define this as m reduced times V, my V is order alpha. It's everybody followed? Okay, I didn't, nothing else. I mean, just plain simple business. So this basically tells you that the electron velocity is very small in the hydrogen atom. Just from the virial theorem, you concluded that the electron velocity is very small, the electron is non-relativistic, the proton is static, and so I can describe in the non-relativistic EFT framework. So this is much, much less than 1. So, so yeah, so basically the goal is now to let's say if you want to describe hydrogen atom, you want to do it. Yeah. So here, oh, you want to understand this one. Let me see, where did I do this? Just give me a minute. Yeah, okay, so I should have written it here. Alpha by R is M reduced alpha square. So the binding energy is M reduced alpha square. This is what I'm using. Yeah. Yes. Yeah, so this condition is what is giving you this part. In the hydrogen atom, potentially, yeah. Yeah.
Then R is 1/MV.
So
these two will get off.
yeah.
The momentum is MV. That alpha is B. Now you have all the scales. So the hard scale, M. There's a small velocity. The next scale is MV. That's the momentum. The next one is the kinetic energy, which is MV.
MV square.
Now in terms of alpha, you have greater than alpha, greater than alpha.
Okay.
Yeah, because it's
I mean, the natural length scale in my hydrogen atom is a Bohr radius. So this is 1 by MV. So, sorry, in what? Yeah, it's the reduced. I mean, the reduced mass is what? Is ME by 2. Yes. The reduced mass is ME by 2. Yeah. Yeah. Yeah, it's still ME. So, I mean, my goal was to eventually arrive kind of this point that V is order alpha, which is the velocity of the electron. And why we are using it non-relativistic is the fact that electron is non-relativistic. And once you define this, you have clear understanding of that this would be MV, which is the relative momentum of the electron in the hydrogen atom, or the relative momentum of the E plus E minus in the positronium systems. And MV square is the binding energy of my hydrogen atom, or the binding energy of the positronium systems. Yeah. You will have to rephrase, like, is there an additional scale that you are talking about? Yeah. I mean, what is the other scale in normal quantum mechanics when we study hydrogen atom? What is the other scale? Yeah, but it is motivated from, I mean, you are matching to something, the system that you know, yes? There is an input that you are taking somewhere. The goal is, like, I could ask you the back question, why in quantum mechanics you solve the Schrodinger equation for the hydrogen atom? Would you give me a first principle argument? You can't give me an argument in non-relativistic in quantum mechanics saying, why did I solve this? It's something we start with this is the Schrodinger equation, this is the wave function, this is what we do. Solving the Schrodinger equation, we get this as the result. Now, in QFT, we are basically showing a rigorous derivation of why the Schrodinger equation comes as the result from all this side. I mean, the QCD, there is the scale of lambda QCD. No, I mean, yeah, I mean, in mesonic system, we have this lambda QCD binding. I mean, you can, yeah, I mean, in a system like QED, you don't have such color degrees of freedom. Yes, there's no color. It's just coming from 1 by R potential. Yeah, this is, I mean, the virial theorem that I used was the classical argument. I mean, I'm not doing anything QFT till now. Once I know what are the problem sets, what is my hierarchy of scale, then I will start constructing my EFT systematically. If I don't know my hierarchy properly, I won't be able to construct my EFT. The goal of the EFT, I don't want to demonstrate here that, yeah, the non-relativistic EFT is always giving you Schrodinger equation. This is true because we are trying to describe non-relativistic quantum mechanics, so you will get Schrodinger equations. That is not the ultimate goal you should take it from. The point is that I can describe my hydrogen atom in full QED, but it's a mess. I mean, you can start with Dirac-Lagrangian, you solve the Dirac-Lagrangian for energy levels. By the time it takes you about 10 pages of calculation to do. But you can construct a systematic EFT in order by order expansions where you eliminate out systematically one scale, then another scale, and then you are only left with the lowest energy scale into your system. In full QED or in full calculations, you will at some point of time have to have there would be log factors associated with high scale and low scale. And then you'll have to do all these log resummations and everything, this more complicated business. Whereas if I go to a low energy EFT, I am only set up at low scale. I fix what is the variable I want to describe, the IR physics. I don't want to think about the UV at all now. I mean, whatever happens to UV, it happens. I mean, it's all absorbed in the Wilson coefficients. Yes, as a byproduct, when we do non-relativistic EFT, we get Schrodinger equation as one of the ways to understand why we did this in quantum mechanics, or why we were solving Schrodinger equation in quantum mechanics. That's the point. I mean, for example, you could describe Rayleigh scattering in QED. It's going to be quite tough. But here in QED, I hope if I have time, I'll get to arrive, but you will just, or we'll describe in tutorial, you will just have one diagram just telling you everything. Just one diagram tells you the Rayleigh scattering process. Yeah. Yeah. But okay, so since you are jumping to that point, let me tell you. So where would the lambda QCD sit? Okay, if you talk about J psi, for example, the lowest germanium and upsilon 1 as bottomonium, lambda QCD, you can show that it's sitting at here, ultra short scale. Okay, you can look at germanium, J psi and eta C mass splitting, compute what is this MV square. You will find that it is roughly around the lambda QCD scale of 300 MeV or 400 MeV, just to give you a sense of numbers. But if you do the same thing for, let's say, yeah, I mean, like Chi-C1P, Chi-C2P, or excited germanium sitting in the higher part of the Cornell potential. So your Cornell potential is here, is like this, yes? Your J psi is at this radius, but your Chi-C1P is at this radius. So this is my R, which is the relative coordinate between the heavy quark and anti-quark. You already see that it is feeling the sigma R part of the potential, and therefore just using the perturbative piece is not good enough. That means my lambda QCD will really sit at this scale, because this is my radius of the bound state problem. And in tetraquark, pentaquark, I can assure you that lambda QCD is even sometimes greater than MV. And then you have to do different method to arrive at the low energy scale. It's called Born-Oppenheimer EFT, but we will not go into that. So, okay. So let me just write down the NRQET Lagrangian. I have 2 degrees of freedom. I have a particle and anti-particle because I'm trying to describe like systems of E plus and E minus positronium type of system. We will not derive it anymore because it's too much. The term in this NRQED Lagrangian is HQET. So let me define two component Dirac spinors. So again, you can recall what I told yesterday. So psi d is my psi chi. This is 4 cross 1. This is 2 cross 1. This is 2 cross 1. Okay. You recall this yesterday that I mentioned, particle, antiparticle. So this is HQET for psi plus HQET for chi. Plus there are terms like psi dagger, chi dagger, psi chi. 4 fermion interaction terms. Because in the HQET, I was only describing a 2-body system with 1 heavy quark. I was not looking at a particle-antiparticle scattering or E plus E minus scattering. Yeah, E plus E minus. So here I have I can look at E plus E minus scattering, and these 4 fermion interactions would come from some diagrams like these. And so let me just quickly arrive at that point. Yeah, so you have coefficients like ds square, ds by m square, psi dagger chi, chi dagger, yeah, psi dagger chi, chi dagger psi. Yeah. Chi dagger sigma psi. So you don't need to be afraid here. I already showed you what is the HQET Lagrangian that we have for the case of quark. There would be an analogous term for the chi. I would have diagrams corresponding to 4 fermion interaction here. So this is one, this is another, accounting for the spin interactions. I would also have terms like minus 1 by 4. Yeah.
Then I would also have the color in this.
Yeah.
Another term.
Yeah. Yes. I mean, basically, there would be TA factors sitting inside. There would be the color index coming from for the quarks. So I have D1 prime F mu nu plus D2 prime by M1 square plus D2 double prime by M2 square or M square, sorry, not M1. F mu nu D square F mu nu. So these are coming from these vacuum polarization diagrams where you have integrating out these electron in the one loop. So, okay, so I really don't have time. I would just want to highlight the power counting here. So I already mentioned so QED, it went down to NRQED. So here I had scales M alpha, M alpha square. Here I have M alpha square. Okay, I have integrated out M. Power counting is that I del is P, which is M alpha. If you use equation of motion, so like the equation of motion that we can, that one can use is just have small time. Psi 0 is M alpha square. And this means that EA0 is M alpha square. Everybody understand? This ID0 is M alpha square, so this means EA is M alpha square. You can again use the number argument. So psi star psi D3 of X is 1, or let's say order 1. This implies psi is psi star psi dagger psi is M alpha cube. And one can also find that EA is M alpha cube. Again, you have to use the equation of motion to get it. So this immediately boils down to the fact that E electric field is M square alpha cube. So this is coming from here, you take the time derivative. EB is M square alpha 4. And yeah, okay, we will see now probably next time. So probably Rishi will pick up from here. There is a lower EFT that we can construct, which is which is called the PNR QED, which will only have M alpha squares. So probably Rishi will describe a bit about it. In the tutorial on Monday, there are two things that we will do. We will together look at why for bound state problems, if I'm looking at, let's say, E plus E minus scattering, and so I have, yeah, so the question is why for bound states, if I have some E plus E minus scattering, why would I need to sum up, if I have to describe the bound state dynamics of the positronium, why do I need to sum up these ladder diagrams? Okay, so we'll just do it from the power counting argument. We don't compute it, but we'll discuss together how from power counting you can really find that the one gluon exchange is at the same order as two gluon exchanges, at the same order as three gluon exchange, which is equivalent to summing up all these diagrams. The simplest analogy that we studied in the literature or had it in this school was, if you recall, Professor David Kaplan, he was describing such type of bubble diagrams on one of the days. And this eventually gives me a bound state. For bound state, I really need to sum up all these infinite set of diagrams. I won't get a bound state from perturbative calculations. This is analogous to this picture here. So we'll do it in the Tuesday tutorial, okay? Sorry, thank you.